Well, hello everyone, and welcome back to Adrian's Digital Basement. This is part 3 in the Southwest Technical Products Corporation 6800 computer system video series. As is always with my multi-part series, I really recommend you catch up on the first parts before you watch this video, and I always put links in the description to all the parts in the series if you're catching up at a later time. In the first part of the series, I took this computer apart and took a look at what was inside of it and looked at a little background of the machine. Then in the next part, I actually plugged it in and turned it on just with a CPU card in there, the bare minimum to get it working. And spoiler alert, it actually did work. So in this part, part 3, I'm going to try to see if I can get this 4K RAM board working, which was one of the original boards that came with this kit when you bought the machine. So without further ado, let's get right to it. So since the last video where I got this machine working, I've been playing around with it a little bit, just trying to get a feel for how it works, because honestly, it's very foreign to me, so to speak. I've never had a machine like this with just a serial console. I'm very much used to things like the Apple II or the Commodore 64, where you have a keyboard and a display output, and as soon as you power it on, it's ready to accept, say, basic commands. This machine is nothing like that. If you want to use basic on it, you actually have to load that into RAM before you can run it. And where we left off before, the only RAM this computer had was the 128 bytes that were on the processor card. So clearly that's not really enough to do any serious work, like run a basic interpreter. So we're gonna have to first test to see if these other RAM cards are working. I wish I could say since the last video I had a wide angle lens for the camera on the bench here, because it would make it a lot easier to kind of get all of this in. But unfortunately, where the camera is right now, what you see on the bench is as wide as I can get it. So it doesn't really show everything. Anyhow, let's take a look at what cards we have here, just as a reminder. So in the machine, we have the main CPU card, which has a little bit of a bootstrap ROM, 512 bytes, has 128 bytes of RAM, and then it has the CPU. And there's also a console card, which actually is very much like this card, which is a parallel card, but it actually bit bangs RS-232 at either 110 bits per second or 300 bits per second. So it's rudimentary, and from my understanding, that original design was based on the ROM chip that's right here on this board, well, down here actually. That is a Motorola supplied part that was part of the development kit that this machine is basically based on. Very much like the Coco or TRS-80 color computer line of machines, or the Dragon, there was a reference design that Motorola had that they offered to companies to use if they wanted. And this machine is very much built off that reference design. So everything about the machine, like the I/O address space, the mapping of the memory, even the boot ROM, is directly supplied by Motorola with no customization whatsoever, at least on this first version of the machine like this one is. So back to the cards we have here. So this is an actual parallel card, so it's got the same chip as the console card, but it actually just exposes the I/O ports right here, and they're buffered through these chips. So this is really like a user port on a VIC-20 or on a 64. And then right here is the 4K RAM board that came with this machine. Originally it would have had 2K on it, half of this, and then the other 2K could be populated later if you wanted. And then this card here is the Smoke Signal Broadcasting BFD68, or Basic Floppy Disk System. And the funny thing is, I'm pretty sure this board was never sold on its own. It was actually sold as a bundle with the external drive chassis from Smoke Signal Systems. And because of that, I think the manual for this was basically included with the disk drive system, the external drive chassis. So I can't find a scan of the manual for this or anything. They made other floppy drive controllers later that basically were updates to this. But this has a 1771 floppy drive controller IC. It's this one right here. From what I've been able to figure out by looking at advertisements for this card and the disk drives that came with it, is it has a 512 byte bootstrap ROM, which is this chip right here. So this is mapped somewhere into memory space, and to get this drive booting, you would have had to turn on the computer and then issue a jump command to whatever memory location this is in. Because when this card was released, there was no standard disk interface system for this machine yet. I'm pretty sure that floppy disks that work on this are not the same as disks that would work on the floppy controller that Southwest actually released themselves. So this will be the last card that I do try in the machine, especially because it's just a big unknown on how it works. And then there is this card here, which is another static RAM board. It's 16K. The manuals do exist for this. It's also made by Smoke Signal Broadcasting, same company as the disk controller right here. Each one of these chips is gonna be 4 kilobits each. So if you add 8 of them, you get 4 kilobytes on a machine like this, which of course is an 8-bit machine. Luckily, because this documentation exists, there are dip switches right here that let you configure where in memory that this maps into, and that is documented on how to configure these switches to map this into different parts of memory. This particular computer, after doing all my reading, can support basically a maximum of 48 kilobytes. The rest of the address space is reserved for the ROMs, like the boot ROM, which is only using 512 bytes, but it could support up to 8K. And then also I/O address space for like those interface cards. So there's only certain spots that this can map into, and I haven't touched these dip switches, so this is mapped into whatever space that this was left on. And then this other RAM card, which was in the machine as well, it does have a little jumper right here, which shows that it was mapped into, I guess, 7,000 hex. So up at the top of that first 32K of memory. Which is odd to me because if you had 2 RAM cards, you would almost want to have a continuous amount of memory. So you'd have 20K total, right? This is 4K, this is 16K. So you would start this at 0000, and then you would have this set to start right at the top of this card. Here's an ad for the BFD68 disk drive system. When it came out, the single drive system, I guess with the controller card, was $795, $1,339 for 2 drives, and $1,479 for 3 drives. And you could buy a standalone disk drive for $360. That would be if you only bought like the 1 or 2 drive and you wanted to add an extra drive. It talks about right here that bootstrap PROM that I mentioned. It says it loads the operating system into a 4K memory board located either 7,000 or optionally at D1000. Okay, and that explains why the 4K memory board is mapped into 7,000 hex, because the operating system that came with the disk drive system required memory to either be there or in D1000. There's actually one more card here. Now, I actually have tested this, so this works. This is a serial card. Now it's different than the one that's in there for the console port because this is a true serial card. This IC right here is made by Motorola and it's actually an RS-232 serial chip. Now the baud rate generator, the clocks for the baud rate, is actually generated on the motherboard and it's sent across a few pins right here on this connector. Now originally it had a little wire jumper link where these dip switches are to select which baud rate you had. Well, I removed that and I have since installed this dip switch block because it just happened to be the right spacing. And then I wrote over here what the baud rates are because originally it was written on the silk screen, not the silk screen, but like the traces underneath where that dip switch is. So you couldn't see it anymore. And as you see here, I have switch 5 set to on, which selects the 1200 baud speed. Now what that does is it just connects the clock to this chip to the appropriate signal on the motherboard that is generated by the CPU card. The CPU card right here has a clock generator or like a clock divider that generates those various baud rate clocks that are available to all the cards on the motherboard. And the reason why they did it that way is pretty smart. And maybe this is part of like the way Motorola wanted you to design it, but it reduces the number of chips that you need. Say you had 2 or 3 serial ports. Well, you don't need to have those clock generator ICs on each one of them because those signals are just available on the motherboard and you just pick it up right off the pins. So it allows like a serial card. Look how few parts there are in here. That's pretty cool. It's a pretty ingenious way of doing it. Okay, I think I've done enough talking. Why don't we give a test to this 4K memory board? Let's see if this works. I think I understand how the memory test routines that are provided work. So first thing to do is just plug this in. And up here on the screen, we have TerraTerm ready to go. I'm gonna hit the power button. And let's see if we get the prompt. Okay. So we got the asterisk prompt. That shows that this machine, at least right now, is still able to run even with this card in there. So this card is not trashing the bus in such a way that it makes the computer not run at all. Okay, so we know based on that jumper right here, this card should be mapped into 7,000 hex. So it's very easy to test with the machine language monitor. Well, you just type M in uppercase, not lowercase, 7,000. I'm always a bit confused on how to use this. So the ROM that's in my CPU card now is the MiniPro. It's the one that was provided by Motorola. So the key syntax is very specific on how you change the memory locations. So you put M7000, and we're gonna look, and it says that FF is stored there now. And I think to change the location, I have to hit space and then type what I wanna have in there. So I put 12, and let's put space 13, space 14, space 15. And if I put a period, no, how do I exit out of this? Space. Okay, I push space without typing anything, and that exits out. So now let's look at 7000 again. There's 12. So right there, we know this card is now working. At least that memory location is good. If I push the period, 13, 14, 15. Look at that. We stored 4 values into this memory card, just like that. Now what's cool is if we go to like memory address 6000, where there's no card in here right now, right? Nothing should be mapped in there. It's currently saying that FF is stored there, but if we try to store something like 12, notice it puts a question mark. And it's doing that because the ROM has a little check routine that after it writes to memory, it reads it back, and if it doesn't see what you programmed in there in memory, then it assumes it's ROM or something else, and it puts that question mark. So that does indicate that this card really does seem to be mapped properly. Okay, so we want to do a more thorough test of this RAM card besides just storing some locations in it. That doesn't really tell us anything. So there are actually some test routines that have been created. Short memory address convergence, so memcom3, modified to work on either MiniPro or SWTPC. MiniPro is the version of the ROM that we have in this machine right now. SWTPC is a later version that Southwest released that has more capabilities. So this document tells you how to use the various test routines, and the memory test routines actually fit into the 128 bytes that are on the CPU card. So you don't need to have any other working memory besides that 128 bytes to test your RAM cards. So that's a pretty cool little feature. Now to run the RAM test, we have to enter that program into the system. Now, if this were like an Altair or an IMSI, you'd have to like use toggle switches on the front, but we have a serial port that we can load programs directly off of. And you don't even need a paper tape reader or a cassette drive to do that. We can just do it through the terminal emulator. On the computer, I have those various RAM diagnostics. There's actually 4 of them here, but memcom is the one we were just reading about. That's the most basic first test. When I open memcom, here's the actual program code right here, and this is in Motorola S records. So all I need to do to load this on the computer is just copy this, go to the terminal emulator, press L, and it puts a space, and I don't push anything else, and now I'm just gonna paste that program in, and there it is. We hit OK. We just wait a second. Now this is going at 300 bits per second, remember? And there it is. Notice how it just went back to the star prompt, so we know that it has loaded successfully. Now we go back to the documentation to see how to use this program. So the section of memory to be tested is set by loading the most significant byte of the lower memory address into A002, the least significant byte into 3, and then the most significant byte of the upper memory address into 4, and then the least significant byte into 5. And then, as far as I understand, once that's done, we just type G, and that will actually start the RAM diagnostic. Okay, so for A002, we're gonna set it to the most significant byte of the start of the memory of this board, and we set it to 7000 hex, right? So we put 70, and then we're setting the next one to 00, so it's going from 7000. So this card is 4K, so the top of the memory that we're gonna be testing is 7F, and then FF. So, oops, I didn't do that right. So I need to set A05 to space FF. Okay, it already was FF. Okay, so now we know if we go to A002, so 7000, 7000, and then the top is 7F, FF. And now we should be able to just type G to start. And look, we're getting little X's. The program is actually running. So it's doing a memory test on here right now. So let's look at what it actually is going to be testing. So the test sequence starts by loading a continuous stream of 256 sequential binary numbers from the low memory address to the high address, inclusive, and then goes back and sequentially reads the data within the locations and compares it what it should be there. If it finds any discrepancies within the memory cycle, 1X is printed and the cycle is restarted. Uh-oh. If it finds a discrepancy, it prints an X. Otherwise, a hash is printed to indicate a successful cycle completion. And look at all those X's. So we have a problem with this memory board. Not surprised. Unfortunately, reading the rest of this documentation, it does not say anything about how to tell what memory is bad on this board. But there are other RAM tests. I think we're gonna have to use one of those. Let's So I just hit reset to break out, and don't worry about this little symbol here. That happens when I push keyboard key press on here. It seems that this card really does not like to handle full duplex communication. The way the bit banging happens on that parallel port, when you push keys on the keyboard while it's trying to print text, you get garbage. All right, so the next test is Cdap, and I think this one, which works the same way, you put the low and the high addresses into those same memory locations. Okay, and this one will stop with a memory address dump, and it will actually show you the address right there of like 400 as in the example, and then it will show you a particular error message here. So in that error message, dual address error low. So the error messages here has a couple, 4 different ones. So let's give this one a try and then see if where it indicates a problem on this board. So same load procedure. Here is Cdap right here. So we're just going to copy that. We're going to type L, and we're going to paste in right here. Takes a little bit longer because, of course, this is running at 300 baud, and it's bigger than that other program, but it should complete. There it is. So the memory location should already be set. Let's take a look here. So 7000 to 7FF. So yes, we are good with that. So we just type G for go, and right away it crashed out. All right, so the error message here, it says the problem is at 7400 and the error code is 7A. And 7A, dual address error high. If the dual address error is found, then writing into one memory location affects another. This explains why that first memory check, when it ran through and wrote a bunch of numbers to it, when it went back to read it, it didn't get what it expected because one of the higher memory locations was affecting one of the other locations in the card. So it put things out of order. Incidentally, a full run of the Cdap program we just ran, when it works properly on a 4K card, takes 7 minutes and 29 seconds to run. We got that error message almost instantly though. We have another memory test called Sumtest here. I'm just looking at the various ones to try to see if we can figure out if we can get to the bottom more quickly on what's bad on this board. It says here that an error message such as Sumtest cycled through 5 times without an error, but on the 6th try, a pattern was used to detect an error. The 06 tells us what pattern Sumtest was working on when the error was detected. So in this error code, pattern number 6. The 20 tells us which bits were in error, and 20_16 converted to binary is 0010000. The location of the 1 is the bit in error, in this case bit 5. Bit numbers start with 0 as shown here. Incidentally, you can use the Windows calculator. You just type in hex, and I typed in that 20 in there, which they have a notation of 20 with a little lower 16 here, and then the binary is right there, 00100000. Also, there's 16A20, that's the address the memory was detected. The IC assignment table supplied by the memory board will help you locate the problem. All right, let's load up Sumtest and give it a run. Okay, that completed. Now let's take a look at the memory locations because there was one caveat. It said to put the upper address as 1 byte plus the actual top of the card. So in this case, we have to make it to 8000. And let's exit out and run the program with a G. Okay, right away it failed out. So this is the output right here. I accidentally hit R, which showed the registers. It looks a little different than what it says here. This says the pattern, the errant bits, and the address. And this has 0080 and 7400. I don't know what all this other stuff is here, so okay. All right, so the pattern, I guess, was 00, and the errant bits was 80, which if we go to the calculator and we type in 80, that would be bit 7. And luckily we can go right to the schematics for the memory board. It's not very clear, but we can see where bit 7 is. Okay, no, it's not there. It's right here, bit 7. So it says IC16 and IC15. So I'm gonna power this off. And I just wanna swap a couple of these chips around and let's see if the error moves. I'm not particularly confident in how good those diagnostics are. So I just don't know if there are actual addressing problems on this board because there's some of this decoding logic here. Is that the problem? Or is it really just simply a RAM chip problem? Luckily in a different PDF here, I think this would have been all one PD or one document originally, but there's 15 and 16 right there, or sorry, it's these 2 chips right here. So what I'm gonna do is I'm gonna swap these with the ones next to it and let's just see if that error moves around. Before I do anything, I'm just gonna put a dot on these chips here, just so I can recognize them and not get them mixed up. So you may be noticing that these videos are just a lot slower paced than normal, and that's just because I'm really learning as I go with this computer. It's quite a steep learning curve, and that's just the way it was back in the day. If you think about computers now, it's like things are so easy. You just open them and turn them on and they work. You just get on the internet in like a minute. And if you think about phones, it's the same kind of thing. They're just so incredibly simplified that it has democratized the computers where anyone can use them. You don't need any skill to do it. Back in the day with this, not only was this a kit you had to build yourself, so you had to know how to do soldering and stuff like that, but even just using it required knowing hexadecimal and being able to understand like program code and whatnot. So things were just different back then. And even me, I'm not quite used to this because I'm much more used to using like a Commodore or an Apple II or even 8-bit machines from just a few years later, which were so much easier to use than this. Anyhow, I swapped chips. I just noticed I swapped the wrong chips. I think I swapped these two chips with those two chips, but I should have been swapping these two chips here. So I'm just going to pop this one out here, and we'll put the two with the dots further away. So I am positive that the dot, which are the original ones on that bit that it's saying are wrong, are not in the original sockets. All right, so the original two chips were this one, and it's now over here and over there. So let's pop this back in. Okay, with the card back in, some people might be saying that maybe I'm having a problem with a dirty connector on the board. That is possible, but I don't think so. And the reason why is because remember, I originally wrote to the various memory locations and it was seemingly working fine. Now, if some of the address lines aren't working properly, it's possible that that could be causing the problem as well. So this could still be dirty contacts on there, but I don't think so. I really think that there's a problem with the chips on this board. All right, so let's power this back on. We got the asterisk, so we know it's working. Here is the Sumtest program, so we'll copy that. We'll push L and we'll load this in, paste. Since I rebooted the computer, we're gonna have to set those memory locations again. So A002, and this is going to be 7,000, and it's going to 8,000. And we exit out of that and we hit G for go. Okay, look at this. Suddenly it's different. So now it's saying that the problem exists on 7,800. And notice it doesn't just crash out like it did the first time. I'm gonna hit reset to stop this. So it's still the same bit pattern, but now it's saying the memory location that's problematic is up at 7,800. Okay, I'm back on the schematics. I think there's a problem. I don't think these are the right schematics for this board. I think there was a later version that had less chips on it, and that's what this is. So we have IC 1, 2, then we have 7, and we gotta scroll to the next page. 9, 11, 15. Okay, so yeah, we only have 16 RAM chips on the schematic. Well, clearly this board's got more than 16 chips on it. It seems to have twice as many. And if we look at the build instructions, which does not have the schematics, so this looks like it has 32 RAM chips on it. So these chips are half as big. So when I move these chips around, I thought I was actually just moving it from one bit to another, so I'd expect that bit pattern to change. So I was confused when the bit pattern didn't change, but the address changed. Because I think on this board, there are 4 chips that actually all have the same bit to them. And you know how we can test that? We could use the multimeter. What I want to do is look at the data pin on these chips and see if, like the ones I just moved around, if they're all on the same data bit. The issue is, I don't know, I have to look up the data sheet because I don't have the correct schematics for this board. So these part numbers are 21L02 SRAM chips. Let's see if we can find that data sheet. All right, and here it is. It's a 1024-bit read-write static RAM. It is 1024 times 1, and that means, of course, 8 of them equals 1 kilobyte, and this is a 4K card, which means 32 of them to equal 4K, which is what this is fully populated. Here is the pin out, and we can see here data out is pin 12. All right, so this chip here has a dot, and pin 12 is common between these two, like the one next to it here. And then pin 12 here, yep, that's common. And this one, it's common as well. So the other dot chip is over here, and that is not common. So that means that it's on a different bit now. Yep. So that kind of tells me that this chip here is almost certainly the problem. I'm gonna move this over into a different spot. So I'm gonna move it right here into this socket next to the other dot chip. Before I do that though, I'm gonna put 2 dots on the one I think is actually bad. Now back to what I was saying is like, I don't have any of these SRAM chips. Now I could try to bodge in like another chip, but I have a better solution for that, and I'll show you that in just a second. Let's just confirm that this chip is bad. Okay, so remember the old error was pattern 0, and the only thing that really changed is it went from 7400 up to 7800 when I moved that chip. So let's hit G. Oh boy, is it actually working now? This is what it's supposed to do when it's working. And oh boy, we're gonna have to run those other RAM tests. These sockets, it could be I just need Deoxit, and I did not put Deoxit on here, I haven't done that. Potentially on old machines, especially ones like this that were exposed to the elements, that's a good preventive measure. If the chips are in sockets, just take them out one by one, Deoxit, but double check you don't bend the pins. It's very easy to bend pins when you put them back in, and then you're gonna introduce another problem that you didn't expect. So the Sumtest obviously is working. This is what it's supposed to do when it completes a cycle. So I'm gonna break out of that with the reset button. And let's try memory convergence test again. This was the first one I ran that gave those X's immediately as soon as it started working. So we're gonna do L, paste, and we do have to change the memory locations because it's slightly different what it's looking for. So that's 7000, just like it was before, but this is 7F and FF. Okay, here we go, go. Hash symbols. I'm back to the original documentation. There's the memcom test. Okay, so it says it prints a hash symbol when the test is completing. Come on, why is it just magically working? This is wild. I don't like these types of weird random issues. I guess my other thought is that maybe it was a bad or loose connection on the bus here. Let me just jiggle this while it's running. See if it stops. No, it's working fine now. All right, let's try that Cdap test, and I'll let it run for the 7 minutes. Oh, that aired out right away. So that one was not happy. Interesting that the other one was working. And it looks like it has moved slightly because I swear that it was originally at 7400 with the same error code here. I'm just gonna swap these RAM chips back to where they were originally. All right, the 2 RAM chips are back in the original location. I don't know if they're swapped though, because I only put 1 dot on each. So if I don't get the exact same results, I will swap them around in those original positions. It changed from 73FF to 77FF. And just for a complete test, I'm gonna swap those back because I just wanna rule out that this is some kind of a strange, dirty pin issue. And it went right back to 3F, or 73FF. So we know for sure that there's a problem with one of those 2 chips. I'm gonna swap one of them sort of like over to a totally different spot on the board. If we do not see any change at all, that will confirm that it's the other chip that is bad. Now what's interesting here is, we're running different memory tests, and you notice how some of them are working perfectly right now. And that's something that's really important for everyone to remember. Memory tests are not super duper conclusive. You can get false readings all the time from memory tests. And that's why there are 4 different memory tests on this particular computer, because they're all very small tests, right? They all fit within the 128 byte RAM on here. And believe me, they're not even 128 bytes. That RAM on here is used up for other stuff too, so they're even smaller. So same on the 64 or any other system, where the RAM test just can give you false readings, or they can say that everything is good when it's not actually good. Okay, so I moved the single dot chip way over here to this corner, and I left the 2 dot one in that original place. Let's turn this back on. All right, and let's hit G for go. Let's see what we got. Okay, it didn't change at all. That tells me it's the 2 dot chip that I left right here that is the problem. That one is causing an issue. Okay, so remember originally this was a 2K RAM card, at least the way it was sold from when you got it with the computer. It would be half of the chips were populated, the other half were just left out. So I could run these memory tests on half the memory here, and it should test good, because I'm pretty sure that this 2 dot bad chip is over in the upper 2K of memory on this 4K card. We can give that a try by just leaving 7000. So we'll just do a little bit of calculation here to figure out the boundary. And this is just to show you how to use a calculator like the Windows calculator. So remember, this card is a 4K card, so decimal, 4096 bytes, that's 4K, which is the equivalent of hex 1000. So remember I said that the memory boundaries were like 0, 1, 2, 3, 4, 5, 6, 7. They're on the 1000 marks. Those are the 4K boundary marks. You have 16 of those in a 6502 or a 6800 like this, and that equals 64K, the total memory space. So to figure out where the 2K boundary mark is, all we do is type in 2048 in decimal, and that gives us hex 800. So the actual boundary is actually at 7800. So this is telling us right here that the memory error actually exists in the lower 2K of memory on here, which is weird to me because I thought the chips over on the right side were the upper memory. So let's just give this a test. Let's test from 7000, so we're gonna leave that 7000 to 77FF, which is the very top of that first 2K. And we're gonna run this, and right away we're getting the X's. So thinks that there's a problem, just like we thought. Because like on the other test, remember the memory location error, can I scroll back here, was here, 73FF. So now if we change the memory locations of the test to the upper part of memory, so 7800, and we're gonna test all the way up to 7FF, that's the upper 2K on this card. Now we hit G, oops, try to exit out of this. Okay, we hit G, and we're getting the hash marks, saying that everything is working. So I just canceled out. Let's load up Cdat again, and let's run it on this upper 2K of memory, and I'm assuming that this should totally work fine. While this runs, because it hasn't printed an error yet, remember it's gonna take quite a while. Let's look at the documentation. So 2K memory test is gonna take 1 minute and 53 seconds. 4K takes quite a lot longer. It's not just like twice as long. It obviously is testing all the memory kind of recursively or something like that. Let's check out the documentation here for the layout of these chips to see which would be the original lower 2K and the 4K. Hopefully it's printed in here. These are the original build instructions for the MP-M, so whoever assembled this would have followed these instructions. It says here that integrated circuits 25 through 41 and the capacitor C9 are not used in this kit. That's the expansion kit for this. So let's look at where IC 1 through 16 are. Oh, and yeah, would you look at that? 1 through 16 is the set of RAM chips on the right of this card. The left RAM chips is the upper bank. And now the diagnostics, so we haven't looked at the Cdat output, we know that it was saying that it was the lower bank that has the problem. That makes sense because remember, I had isolated to this double dot chip right over here. The single dot chip over here, I said was fine. The double dot chip is, I know, the bad one, and it is in the lower bank right now, which coincides with the information we're getting on the diagnostic. Okay, while we're looking around, it completed, no error messages. So Cdat is working. So we know that the upper 2K on this card work, but that chip right there has gone bad. Now, this is the bad chip. I'm curious, does the Retro Chip Tester Pro actually test this type of memory chips? Let's give it a try. Now, I'm sure even if this does not test it, it probably can be made to test it because there's nothing special about this chip. It's just a TTL chip. All right, here we go. There it is. It tests bad. Let's just pop a different one in here just to double check that it tests a different chip and it has no problem because, you know, maybe it's incompatible in some other way. Okay, so here's another one. Let's pop this one in. Look at that. It's testing great. Okay, confirmed. One bad SRAM chip. Test passed. All right, so with this board, we know this chip is bad. I'm just gonna draw an X on it here, like that. I think the rest of this board actually works. There are no other problems with any other RAM chips on here because we moved that around. It seemed to follow the problem, and we know that this part of the board right here is working perfectly. We ran the Cdat on it, and I guess I could take a RAM chip from there, stick it over here, and we could double check that. I'm just gonna do that really quick. I wanna rule out that that is the only bad chip on here. Now, while the diagnostic runs, it would have been possible for me to try to reverse engineer this a little bit better because not having the original schematics did kind of suck. It would be certainly nice to be able to look at the memory location and be able to figure out exactly which chip on here was the problem. As if all of these chips were soldered on the board, it would have been a lot harder to just swap them around to try to figure out which was the bad one. Okay, so the diagnostic just finished, so that does confirm that all of the other RAM chips on here and the SelectLogic is all working perfectly. That's not bad. I really had a feeling that this board wasn't gonna work properly, and I figured there were gonna be multiple chips that were bad. So just to have one, it's not as bad as I thought. All right, I'm gonna have to end this video here. I want to be respectful of my viewers' time, and I know that some of my viewers do love the long form videos, but generally those don't do very well, and it's better for me if I actually break them up into little sections that make a bit more sense. So we did figure out in this video, indeed, that this 4K RAM board does have a bad RAM chip in it, but it can operate fine as a 2K RAM board when you're only using half the chips. And unfortunately, 2K of working RAM is not really enough to run some of the cool programs that exist for this thing, like the basic interpreter, which is really the one thing that I want to use the most. Seems that the minimum amount of memory that any of those require is 4K, so with this, it's just not going to work. So in the next video, I'm going to show a couple things, including a handmade RAM expansion board that I made, and we're going to try to get that other RAM expansion board, the 16K smoke signal broadcasting RAM board, working. So get subscribed if you haven't already, so you can see that part when it comes out. And now for some channel housekeeping stuff. Of course, thumbs up if you liked this video, but if you didn't, you know what to do. Don't forget to check out my second channel. I have interesting videos over there, including a look at another interesting 70s machine that I got at the same time as this PC. I want to thank my patrons. Their names are scrolling up the side of the screen. If you want to become a patron, you can do so at the link in the description below. My patrons get early access to videos, plus I post the occasional Patreon exclusive video for the higher tiers. It's all explained on the Patreon sign-up page. And lastly, I want to mention that I do have a merch store now, which right now just has t-shirts on it. So there's a link in the description to that as well if you are interested in any of that. And I guess that is going to be it. So stay healthy, stay safe, and I will see you next time. Bye.